Good morning, good afternoon, everybody. Thanks for attending our polymer activation feed system parts maintenance and sizing webinar. Paul Plackey is going to be our presenter. Before we get started, I want to go through a few housekeeping. We are going to be sending out a certificate of completion tomorrow, probably about the same time right now at 1 p.m. It's an automated system, goes through GoToWebinar. You should have everything you need on there for PDH credits. Next month, we're going to be doing another webinar, and that webinar is going to be somewhat related to what we're going through today. It's going to be on sludge vision, and we'll be in luck because Luke's going to be back doing that presentation. So be on the lookout for some emails from me in the coming days and weeks on that. Should be probably around the third week of May, give or take. With that said, I'm going to hand it over to Luke and have him go through the webinar. There is going to be room for questions on the end, and the inside of the GoToWebinar app, you should see a questions with a question mark symbol on it up top. Please use that to ask questions, and we will definitely go through that at the end. Luke?
Excellent. Thanks, Mike. Appreciate everyone joining. Good morning, good afternoon, wherever you are. As Mike said, my name is Luke Plackey. I'm not Paul. Paul's my dad. I think he's on listening, so hi, Dad. I'm happy to have you here today. I'm the Western Regional Sales Manager for Clean Water One. I specifically cover chemical feed products with expertise in design, sale of polymer blending feed equipment. So thank you, everybody, for joining us. Excellent. So for those of you who joined the polymer activation webinar, some of this stuff is going to be a little bit similar. So it might be a little bit of a rehash, but in terms of this presentation, we're really going to be looking at it more towards the aspects of operation and maintenance. So today we're going to be covering very quickly just what is polymer, a little recap on what is polymer, why we're using it, the different types of polymer that are on the market. Then we're going to jump into some design considerations. We're going to look at equipment sizing. We're going to look at pump selection, water quality requirements, storage options. And then finally, we're going to end with some operation and maintenance tips and kind of focus in on a few key parts of the polymer systems that may be an area of focus for maintenance. And then finally, like Mike said, we should have plenty of time for questions here. I can't get through all of them, but I'll definitely do my best to answer as much as I can in the time we have. We're going to have a couple of polls throughout this presentation, everybody. This is really helpful for us. So if you would, please just take a second. Let us know, what best describes you. Are you a consulting engineer? Are you at the plant level, maintenance supervisor, operator? If you could let us know, that would be excellent. So moving forward from the poll, we're going to quickly discuss what is polymer. Why do we use it, right? This is important for understanding the system altogether. Polymer is a large molecule composed of multiple monomers, each of which have a charge. The goal of the polymer is to attract solids using its charge, and the polymer generally has the opposite charge of the solids it's trying to attract, or not generally, it always does. This process of coagulation is used to enhance the flocculation, clarification, thickening, and dewatering process. The best way to think about it is this polymer is added to aid in the thickening, dewatering, settling process by removing the solids from the water. When we're referring to polymer, it can be used kind of generally in a lot of different terms, but there's different types of polymer. We have what we often refer to as neat polymer, liquid polymer. Those would be our emulsion and dispersion polymers. Those are very similar polymers. Really, the main difference between those two is going to be active content of that polymer solution. So an emulsion polymer is generally around 25 to 40% with a viscosity of around 3,500. It's opaque in appearance. Its active ingredients are polymer, oil, inverting surfactant, and water. The difference between dispersion and emulsion, again, active content, right? So we're looking at a 40 to 75% active content for those dispersion polymers. Viscosity is up to 5,000 centipoise. Same primary ingredients, polymer, oil, inverting surfactant, and then generally that appearance is more white in color. Manic polymer, we're not going to talk a lot about this today. It's a very specific type of polymer and it's a very specific process. But just for everyone's reference, it's generally a clear, highly viscous solution. The only ingredients in there are polymer and water. Its viscosity can get up to 100,000 centipoise. and its percent active content is generally around 3 to 8%. This another word for manic polymer that can be referred to as a solution polymer. So the best way to think about this is it's pre-activated polymer in solution, which is why it's so viscous and you have such a low active content. And then finally, there's dry polymer, right? So that comes in beads, granules, fines, primary ingredients in there, polymer. Viscosity, it's a dry chemical, and then active content, depending on the purity from the supplier, it's around 100%. Second poll of the day, be interesting to understand, if you are at the plant level, what type of polymer are you currently using? Are you using emulsion, dry, or manic polymer? When we're looking at selecting or designing or even the maintenance of a polymer system calculations are extremely important. There's a couple things that we're going to be looking for when we're sizing these pieces of equipment. They can differ between dewatering and thickening and clarification and flocculation or filtration. So we kind of broke it out here to kind of look at the key aspects of the sizing criteria that we're looking for to size these systems up. When we're in reference to dewatering and thickening, we're looking at the flow rate of the sludge going to the dewatering or thickening device. And of that sludge, we're looking at total percent solids incoming. Then we need to understand the dosage rate of the polymer, right? But the caveat there is we need to understand whether we're looking at that as an active or a neat basis. If you look over to the chart on your right, this is an emulsion polymer sizing sheet that we use for neat polymer. And you'll see that there's actually a line in there to input your active polymer content. Inputting your active polymer content is then going to convert your neat polymer flow into total neat polymer flow or volume of flow. So again, when we're looking at the sizing of a liquid emulsion system, it's really important to understand that active content because generally when we're referring to neat polymer, that active content has already been taken into account. If we're referring to active content, there's additional steps we need to take. And then finally, we need to understand the solution concentration of what we're feeding to the process. In reference to clarification and flocculation, we're really looking at two things. We're looking at the plant flow in MGD, and then we're looking at the estimated polymer dosage in parts per million. So we talked a little bit about percent solids, incoming solids. There's general guidelines for the typical concentrations of sludge going to thickening and dewatering. Generally, if this is like an existing plant, this is going to be known. But if it's a greenfield or an expansion where maybe there's not any sludge to test, there are general guidelines we can use. So dewatering typically has an incoming sludge percentage of around 2 to 4%. Thickening typically has an incoming sludge percentage of around 0.5% to 1%. And clarification and filtration is quite tricky because it can vary pretty widely, but it's expressed as milligrams per liter of solids. The other thing that we looked at in that chart, in that sizing chart above, was our dosing rate, right? So our dosing rate is expressed as pounds of active polymer per dry ton of solids. This is generally needs to be determined through bench testing, right? So this is something where a polymer manufacturer, the manufacturer of the actual chemical itself, generally will provide this service for free. They will go out, they'll have them send a sample in, or they'll go out and they'll take samples. And then they'll do different jar tests with different types of polymer to really nail down the different polymers to use and then the dosage requirements for that specific sludge. It's really important to note that like different sludges can require vastly different polymers and vastly different dosages. So a primary sludge is much different than an ATAT sludge. Aerobically digested sludge is going to be much different than any of the other ones as well. So the really nailing down your specific dosages based on jar testing is really important for the final design. Sometimes during early design, when this information isn't available, we need to make an estimate. There are guidelines. Generally, dewatering is around 15 to 40 pounds per dry ton. The general number that I use when we don't have that jar test information for dewatering is around 25 pounds per dry ton. And then thickening, you're around 5 to 20 pounds per dry ton. So this can always help as far as the initial design of these systems, but it's always important to really get that bench testing done so that we know specifically what type and what dosage of polymer we need to be using. The dosing rate for clarification and filtration is much more tricky. It's expressed as parts per million or milligrams per liter. And this generally needs to be determined by process equipment manufacturer and bench testing. You can see we have a general guideline of 1 to 10 parts per million, but that's actually a really wide range, right? So we can kind of have an estimate in there to begin with, but again, it's really important to nail that down further along in design. And then finally, what we're looking at here is concentration. What concentration are we sending to the process? And that concentration can differ depending on the application. So as you'll note, there's again general guidelines here. Clarification, you're looking at around a 0.1% concentration based on neat polymer, thickening around a 0.25% concentration, and dewatering around a 0.5% concentration. This is important because the solution concentration not only affects the process, but it can affect how well the solution mixes into the process you're feeding it to. So another way that you can think about the solution concentration is we're really trying to match the viscosity of the treatment line that we're feeding it into, right? So if we're feeding into clarifier or filter, we're really feeding it into basically water, right? So at that point, we're making down a very light solution concentration to match the viscosity. As we bump up to thickening, we're injecting into a bit of a thicker sludge at point, again, around a 0.5%. And then dewatering, the process flow gets a little bit thicker, so we're going with a little bit thicker viscosity there as well. That aids in the mixing of the polymer solution with the sludge. The other important aspect of a solution concentration as it pertains to design considerations is that solution concentration errors can directly lead to maintenance issues. And we'll talk about that in a little bit. Dosing errors. So this is a big one. This is something that at a plant level, if you're seeing signs that of some of these that we're about to talk about, you might be overdosing, right? So signs that dosages may be off in your operation. The first and most easiest to identify is performance issues, right? You're not getting the proper performance out of the system that you would be expecting. That may lead you to determine that their dosages may be off. One of the things that we'll see with overdosing is a foamy centrate or filtrate, right? So generally that's polymer escaping into the centrate and it causes foaming. And then finally, we'll also see gelled or shiny sludge. So if too much polymer is used, you can actually see the sludge starting to gel and it turns shiny. The other thing we can look for is effects in other areas of the plant. Overdosing can cause blinding in your filters or floaters in your clarifiers as that centrate is sent back to the head of the plant. So overdosing may not only affect the specific process that it's being used, the polymer is being used for, but it can also affect other areas of the plant. And these are important things to look for to help identify maybe some dosing errors in the process. So when we're looking at polymer systems, and we looked at the sizing, but now we want to look at different design considerations as far as what pieces of equipment are we using to build these skids. One of the big ones is pumps, right? So all of these skids, whether it's an emulsion polymer system or a dry polymer system, it's somewhere in the process it's going to have pumps. Neat polymer pumps and solution metering pumps are generally going to be between 3 types of pumps, which is progressive cavity, peristaltic, and diaphragm. The recommended option for emulsion polymer and solution metering pumps for dry polymer is progressive cavity. These are excellent with high viscosity polymers when we're in reference to a neat polymer. They're really reliable, less prone to plugging due to polymer agglomerations, and those can be a naturally occurring agglomerations in your neat polymer supply. So they do a really good job of passing those agglomerations without plugging. The other benefit of these, you have a really robust design, and then you do get a pretty good 20-to-1 turn down out of these pumps. So this is generally the standard that we use when we're building neat polymer pump systems. And then even for our solution metering pumps, we tend to standardize on these progressive cavity pumps as well for those reasons. Another option that we will see is peristaltic pumps. These are kind of cool because you can have an integral motor and controls, but they do require tube leak detection. We want to know immediately if something happens to that tube, if it breaks, if it's leaking, because it can cause a gigantic mess if we aren't able to shut down that pump. One of the downsides of using a peristaltic pump is for a high-end peristaltic pump, they're generally much more expensive than a progressive cavity pump. And in regards to neat polymer, they can be prone to plugging due to the small inner tube diameters. Again, any little area, any pinch point, any small tolerance area, neat polymer has a way of getting in there and potentially plugging it. In regards to solution metering pumps for a dry polymer system, depending on your flow rate, these pumps can get very large. So footprint is something to consider there. And then again, the cost of these pumps at those large flow rates as well can get very high. One of the other considerations with peristaltic pumps is selecting the correct tubing. Tube wear and tear needs to be considered. Generally, you're going to require a specific type of tubing for the polymer being fed. And that's also, it's really important, right? Because we can get into an issue where tubes need to be replaced quite frequently, and it can cause maintenance and operational concerns. And then finally, the diaphragm pump. This is an excellent pump for so many different chemicals and so many different applications. It's just really not the right pump for neat polymer. It's not recommended due to maintenance issues with viscous polymer. They have really small ball type check valves in the inlet and the discharge. And again, neat polymer has a way of finding those little areas and clogging it. And what we've seen just in our thousands and thousands of installations is these can potentially cause maintenance concerns and headaches with the amount of plugging and maintenance required to clean them. So we generally try to stay away from diaphragm pumps for neat polymer applications. Again, it's a great pump for so many different applications. Neat polymer is just not really one of them. So regardless of what pump we're using, these pumps require flooded suction with neat polymer. And that's due to the viscosity of neat polymer itself. The published suction lifts on these pumps are based on water. So, even though you can get a 2.5-foot suction lift with a progressive cavity pump, that's based on water. So we always want to have the polymer supply either at or above the suction of that pump. And then if the pump is to pull a suction, if it's absolutely required, a special shaft seal is required. It's really important to kind of avoid this at all costs because it basically makes the pump work a lot harder. And again, maintenance and operational issues can happen. You can burn out stators if you run dry. The motor's working harder. So we really, really recommend for reliable operation flooded suction. The other interesting thing about neat polymer, as we talked about how the static viscosity gets 2,500 to 5,000 centipoise. It's actually a non-Newtonian fluid. So viscosity of polymer changes as it's being pumped. So 2,500 centipoise neat polymer maybe only be 250 centipoise when it's being pumped. Another consideration there, an interesting fact. One of the questions that we get quite frequently is water quality. What type of water can I use for my neat polymer system or my dry polymer system? The question of what is acceptable for water quality for a make-down unit is really difficult because poor water quality affects different polymers in different ways. The fact is, however, that more solids and more chlorides that are in that supply water, the worse the make-down quality is. We've done a lot of extensive have discussions with polymer manufacturers, different polymer manufacturers, and we've come up with some general guidelines, right? So when we're talking about solids, we want to look below 50 milligrams per liter. Chlorides is a little bit of a tough one. We've received widely ranging responses from polymer manufacturers. Generally, the response is below 10 milligrams per liter. But what happens is chlorine actually cuts the molecular weight of any polymer at the part per million level. So it actually degrades that polymer. Conductivity, we're looking at below 1,000 microohms. Sulfates below 200. We already talked a little bit about the solids level, but this is important. It has a minimal effect on the overall polymer itself. But what it does is as soon as those solids come into contact with the polymer, the charge sites on that polymer molecule start to be taken up. This is a big one because another question we get is, can we use potable water? Can we use reused water? Ideally we're using potable treated water, but in many cases that's just not available or it's not feasible. So, many instances, plants are using recycled water or non-potable water. There's just different considerations we need to take when we're looking into that. One of those would potentially be a filter, right, to filter out any organic material or any solids that are in the water. And we'll touch that in a little bit here when we talk about different components of the polymer skids themselves. So polymer storage, this is just something that every plant has to deal with, right? How is the polymer being delivered to site and where is it being stored? When we're referring to emulsion polymer, generally there's three ways to do this. We can use polymer totes, we can use polymer drums, and we can use polymer storage tanks. What type of storage we're using depends on the rate at which we're using that polymer, right? So for smaller applications, we may be using a polymer drum. Medium to large applications, we're using totes. And then for very large applications where we require a lot of storage, we're going to be using polymer storage tanks. For each one of these storage devices, mixing is really important. As we talked about, polymer is made up of oil, water, and vernier surfactant. And what can happen if that polymer sits is it can actually stratify. The solids of that polymer will drop to the bottom, and that can cause major maintenance issues as well as dosing issues. We talked about those naturally occurring agglomerations that may happen in that neat polymer supply. And when you have everything sink to the bottom, it can get really gunky and it can cause plugging issues for your pumps, your check valve, pretty much everything downstream. So mixing is really important. Generally on totes and drums, we're seeing mixers. So that these would be specifically designed to turn over a polymer tote or a polymer drum, but we need to do so without damaging that polymer, right? So when we're selecting a tote mixer or a drum mixer, we need to do the research on, what type of impeller is this using? Is this low RPM, larger blades, multiple impellers? We want to be able to turn that tote over effectively without damaging the polymer in doing so. With polymer storage tanks, we have a couple different options, right? We can use a tank mixer or we can use recirculation pumps. Both options can be used. With recirculation pumps, there's design considerations there as well. We want to have the rate of that pump be fast enough that we're actually mixing the tank. If we're pulling out of that tank at a low rate and putting it back in the tank, we're really just taking the polymer that was on the bottom and putting it right back on top, right? So we want to make sure that we're recirculating that tank fast enough to actually get that tank to mix. Depending on the tank size, like for a 8,000 gallon bulk storage tank, generally that recirculation pump is going to be around a 50 gallon per minute pump. Those pumps do not need to run constantly. Generally, they will come with a timer, so you can set it. It'll run for a specific amount of time, maybe once a day, maybe a couple times a week, right? The whole idea here is just to keep that polymer solution homogeneous to help keep everything flowing and performing well downstream. Dry polymer storage, there's a couple more caveats to this. Generally, that we're going to be seeing three different types. We're going to see 50-pound bags for smaller applications, bulk bag or super sack for a little bit larger applications. And then for really, really large applications where we're using a lot of polymer, we may look at a silo. 50-pound bags, bulk bags, and silos all have specific requirements, right? And it's a good thing to consider when we're designing a system is how are we unloading these 50-pound bags into the hopper? How are we unloading these bulk bag systems or bulk bags through the untie box into the hopper? And then silos, how are the trucks pulling up to these silos? How are they unloading into the silos themselves? One thing that we want to consider with these 50-pound bag systems and bulk bag systems is dusting, right? We want to look at systems that have the ability to really maintain dust as much as possible. For a 50-pound bag system, that may be a dust collector on your hopper. So when you open up that door, the dust collector kicks on and it's actually drawing air into the hopper. So when you're cutting your bag, or the operator's cutting the bag and dumping it, you're getting reduced dusting from that process. For bulk bags, how are we untying that bag into and letting the polymer flow to the hopper? Looking for a system that has an enclosed untie box. Anything that can help enclose and keep the dust away from this process is going to be really important for operator safety. as soon as polymer gets wet, like dry polymer on the floor, as soon as it gets wet, it's very, very slippery and it's hard to clean up, right? So we want to eliminate dusting and spillage as much as possible. Other storage considerations for dry polymer. Dry polymer is extremely hygroscopic, meaning it attracts water very, very easily. We want to keep these bags in a temperature controlled environment and preferably a humid controlled environment as well, humidity controlled environment. If that polymer is fouled due to excess moisture or improper storage, maintenance issues definitely can occur, right? We can see clumping, we can see feed issues, and then you're also not going to get, effective wetting and activation out of that polymer itself. So keeping these dry polymer bags in a climate controlled environment is really, really important for the overall process and maintenance. All right, before we start jumping into specifically, emulsion polymer skids and dry polymer skids and maintenance and operational concerns, we'd like to know, what is the biggest concern with your current polymer system? If you could pick one thing on your current polymer system that causes you the biggest headache, what is it? As we're finishing that poll, we're going to jump into system operation and maintenance. We're going to start with emulsion polymer systems, and then we'll move into dry polymer systems after that. And before we get into the emulsion polymer systems, I wanted to provide some examples of general layouts of emulsion polymer blending skids. So on the left there, you have your hydrodynamic non-mechanical blending skid. In the middle, you have your mechanical skid, and then on the right, you have your hydromechanical skid. The differences between these systems really come down to how we are deriving our mixing energy. The non-mechanical system, that system is using water pressure to derive the mixing energy. With the mechanical system, it's using an impeller. And with the hydromechanical, it's using both water pressure and an impeller. What you'll notice, though, is that many of the components on these skids are very much the same. You have your neat polymer metering pump, you have your solenoid valve, you have your water flow meters, you have your check valves, and then you'll have your calibration column as well. So though the mixing chamber designs may be different, many of the components on these skids are very similar. When we're talking about a mechanical or a hydromechanical system, one of the maintenance points here is the mechanical seal, right? So this is the seal between the mixer shaft and the impeller. As good of a lubricant as emulsion polymer is when it's wet, it can really become a glue when it's dry. And what can happen is if you're operating a system and then you shut down for an extended period of time and that polymer dries on that mechanical seal, once you start the system back up, it could potentially crack that seal. So there's a couple different options for this. Some of these systems have what's called a seal flushing system. So it'll automatically flush the seal anytime the polymer system is in operation. But I always recommend, as far as spare parts for these polymer systems go, to have an extra mechanical seal on the shelf. We'll get into it here in a second, but flushing and cleaning is really important to help remediate the issues with the mechanical seal as well. The check valve, this is a big one. This is a major pinch point for any emulsion polymer system. This is the part of the system where the polymer is being injected into the mixing chamber. As we've talked about, neat polymer itself can be gunky. It's very viscous and can have naturally occurring agglomerations. There's many different types of check valves. This one in particular, I used this drawing because it was the best drawing I had. But essentially, we want to be able to easily access and easily clean these check valves. We also want to make sure that we have spare check valves on the shelf. These check valves are designed to pass the smaller occurring agglomerations, right? So these smaller naturally occurring agglomerations, we're hoping that we can get these through these check valves. Over time, with buildup, with different types of polymer, you can get agglomerations in the mixing chamber, and it's very important to clean, the check valve. So it's very important to clean this check valve. One of the things to look for when designing a system or selecting a system is, where is the check valve and how easily accessible is that check valve? Again, as far as spare parts go, this is my number one. We want to have a spare check valve on the shelf. This will allow you to basically remove the existing check valve, place the spare shelf check valve on the system. Generally, this takes only 30 seconds to a couple of minutes to do. And then you can clean the check valve that was on the system. And it's really important to let that check valve dry completely before it's introduced to polymer again. As soon as, if there's any moisture left in that check valve, the water will react with that and it'll start to gel. So the check valve is a really important maintenance item. It's really important to be able to have access to this check valve. And it's really important to have a specifically designed check valve that's for neat polymer itself. The solenoid valve. So when we were talking about water quality and different items as far as water quality goes, solids is one of those things that came up, right? So the solenoid valve is responsible for turning on and off water flow to the system itself. One thing that's important to note here is that buildup can happen within these solenoid valves if there's a high amount of solids in the water. And what can happen is that plunger can get stuck open. So these will fail open. And basically, it eliminates your ability to shut the water flow off unless you have an isolation valve upstream. So making sure that we have the correct water requirements for the system is important. And when we do have a certain amount of solids in the water, it's a good idea to start considering some sort of strainer upstream to collect any biological growth in the lines or any solids that are in the water itself to help this solenoid valve operate efficiently. There's a couple different items that are common between all of these skids, and one of them, depending on the different control options of the system, is a differential pressure switch. So this is essentially used to sense differential pressure of the system, and it's used to shut down the system on loss of water pressure or flow. It's important to understand, though, how to calibrate these, right? They come out with a factory preset of around 15 psi. These are adjustable. So in order to adjust the pressure settings, you can turn that nut clockwise or counterclockwise to increase or decrease the pressure. This is something that we may need to consider if the system is tripping out based on water flow, but that's also something that we would want to look at. Why is our water pressure so low, or do we need to increase it in some way? But anyway, it's good to know that this is adjustable. And in the manuals, there's really straightforward step-by-step instructions on how to do so. Another item that is really common for these systems is what's called a thermal flow sensor. And the purpose of this sensor is to sense polymer flow. This thermal flow sensor will shut the system down upon loss of polymer flow. This is really important because this device helps protect the pump. For example, a progressive cavity pump cannot be run dry. So if the system senses a loss of polymer flow, it's going to shut down the system automatically. These do need to be calibrated. They're calibrated out of the factory. However, every now and then they need to be calibrated in the field. Basically, what we're doing is we're setting these teach points, the low and high teach, based off of the pump rate. And so the specific pump rate is going to dictate what settings this thermal flow sensor is at. Every now and then these do need to be calibrated. Another really important aspect of these is because it's another pinch point, they need to be cleaned. Cleaning frequency depends on a whole bunch of different factors, right? Type of polymer being used, amount of agglomerations in it. These are really easy to clean. They basically thread out, you wipe them down, you place them back in. A lot of the times when we see issues with, system faults or something like that, it's this guy and it's this guy needing to be cleaned, and it's a really easy fix. So something to keep an eye on as well as being able to calibrate this thermal flow sensor. One of the best things that we can do for any emulsion polymer system is having a flushing and cleaning schedule, right? So when these systems are in constant operation, it's important to keep the components clean, but when we shut down the system, it's also really important to flush this system, right? It's important to get the neat polymer out of the pump line. It's important to get the solution out of the downstream plumbing so that it's not sitting there. And one of the things that we can do with that is flushing. There's a bunch of different ways to do this. My recommendation is we can add a flushing cycle, which essentially is a little timer. It keeps the solenoid valve open. So when the polymer system is shut down, the solenoid valve will be set open for a preset amount of time. It allows water to flush through the system, the mixing chamber, and the downstream plumbing. The other consideration, however, is flushing the pump. Again, this is relatively easy to do, but it's really important, especially on shutdown. What we can do is we can fill the calibration column, which you'll see on the left-hand side of those first two skids, and on the skid on the right is in the back. You fill that with mineral oil, and there's a couple ways to do it. You can isolate the polymer inlet and open up the calibration column and pump the calibration column through the neat polymer metering pump. Generally, you're going to want to do that a few times to flush everything out. The other way to do that is basically create a recirculation line. So you're taking the basically a line from the discharge of the pump into the top of the calibration column. You open those valves and you're cycling that fluid, that mineral oil through the pump to help clean it. It's really important that we use mineral oil here. We do not want to use water. Again, it's the same aspect that we talked about with the check valve, where as soon as polymer is introduced to water, it starts to react, right? So we can cause plugging all over. So cleaning procedures for anything that is in contact with neat polymer needs to be done with mineral oil. So we talked about emulsion polymer systems. Now we're going to jump into some dry polymer system maintenance and operation considerations here. So again, first off, let's take a look at some dry polymer systems, get familiar with these guys. There's really two schools of thought when it comes to making down dry polymer. Again, the components of these systems are very similar. You have your hopper, your feeder, your tanks, your mixer. Really, the difference between these systems is going to be how we are wetting the polymer. On the left side there, what we have is called a shower type wetting head. This system uses pneumatic conveyance to blow or convey the polymer up to that tank top wetting head. In that wetting head, there are spray jets that are spraying a 360-degree pattern, and that polymer is wetted as it's dropping down into the mix tank. The system on the right is what we would call mechanical mixing bowl assembly. This system, the volumetric feeder feeds directly out of the hopper into the wetting bowl assembly. Within that wetting bowl assembly, there's a cyclone of water, and then there's also an impeller in there to help create high energy mixing. The different types of systems require different types of maintenance and different types of cleaning. When we're looking at the different mixing chamber or mixing wetting designs, again, there's shower type designs, there's wetting bowl designs, and these require different amounts of systematic cleaning. What you'll see in the top right, and I don't expect everyone to be able to read all those little bullet points, but there's a couple of things that are important to point out here on this wetting bowl design. One of the things, and the first thing is you'll actually see this, you have your volumetric feeder screw, that orange part, or excuse me, that yellow part right there. It's feeding the polymer into the wetting bowl. When this system shuts off, it actually has a plunger. And what that plunger is doing is it's closing the discharge of the volumetric feeder. The reason that's important is because this wetting bowl is an extremely humid environment, right? You have your water sitting directly below your discharge of your feeder. And if you leave that discharge open, again, polymer is very hygroscopic and you can get plugging or bearding off of this volumetric feeder discharge. The other thing I want to point out here is that this system actually has a mechanical mixer in it. So you'll see other types of dry polymer systems that are purely non-mechanical wetting cones or wetting bowls, where you have a cyclone of water, you're dropping that polymer directly into that cyclone of water. That is where your wetting happens, and then it's adducted up to the tank top. This system has a mechanical impeller to apply ultra-high mixing energy. The reason that's important is for systems that don't have that mechanical mixing energy, at really, really high flow rates, you can potentially get plugging issues. So one of the things that we also want to look for in here is, do we have a level sensor for an overflow sensor in that wetting bowl? As far as design considerations, it's important to look for wetting bowl systems that have the added features such as that plunger to close off the volumetric feeder discharge, as well as that mechanical impeller to induce high mixing energy to more properly wet and effectively wet that polymer as it goes to the tank. When we're talking about a pneumatic conveyance system or a dry polymer system with the shower type wetting head, there's really two items of focus here. And one of them is the feed funnel. So this is where the polymer is being fed from the volumetric feeder into this feed funnel. It is not exposed to any water, and it is heated. However, depending on the amount of fines that are in the dry polymer supply itself, they can build up. So it's important to be able to have access to this feed funnel and to clean it as well. Same concept with the wetting head. It's important to be able to have access to it and to be able to clean it. depending on the amount of fines in your system, depending on the quality of polymer, the cleaning frequencies may vary. The backbone of any dry chemical feed system, or in this case, a dry polymer system, is going to be this volumetric feeder, right? This is where we're metering or distributing our polymer to the wetting device. Some things to look for on the volumetric feeder, right? We want to look for easy tooling change out. We want to make sure that there's material conditioning devices. In this case, you'll see that there's a vibrator on the side of the hopper to help facilitate flow to the auger itself. And then you also see that there's a material conditioning overwind there. Again, that helps facilitate flow to the auger. We want to look for proper auger sizing. This is incredibly important, right? We don't want an oversized or an undersized auger for the amount of polymer that we're feeding. This goes back to easy tooling change out. So depending on your feed rates, it's really important that you're able to switch out these augers if required, depending on your different feed rates for the plant. We want to look at proper tolerances. And the tolerance that I'm talking about is really between the auger and the discharge spout. We want to make sure that's specifically designed to be able to feed accurately. What can happen is if we have too big of a tolerance, you can get inaccurate feed rates. You can also get flow through that feeder. But if you have too tight of a tolerance, you can get really annoying squeaking, you can get grinding, you can get, maintenance issues with that as well. Cleaning access is another really important aspect of these volumetric feeders. We want to have access to clean them, whether that's a hatch on the side, a hatch on the front, some sort of ability to get into this feeder. And then another consideration for the system overall is some sort of isolation above the feeder, right? So if we do need to change some tooling out, if we do need to clean that feeder, we need to be able to isolate the polymer supply from the feeder itself. For dry systems, solution metering pump, critical part of the process, right? This is what's delivering that properly wetted, properly mixed, properly made down solution to the process. Couple design considerations here. Pump selection, we talked about it. It's a little bit different. The requirements are a little bit different with dry polymer. Peristaltic pumps may be used a little bit more often, but again, we do generally standardize on progressive cavity pumps. But we want to make sure the pump sizing is correct. We want to make sure the pump turn down is correct. And then for those peristaltic pumps, we want to make sure that they have run dry protection we want to make sure they have tube leak detection. And then we want to have run dry protection for progressive cavity pumps. This is an item where it's really important to have spare parts on hand, right? A spare stator for a progressive cavity pump, a spare tubing or tube head for a diaphragm pump or a peristaltic pump. So design considerations really come in hand here as far as sizing, turn down, and maintenance. So what is the best way to address maintenance and operation concerns? Really, the best time to address the concern is before it happens, right? So we want to try to maintain the equipment to the point where we're not having reoccurring maintenance issues. Routine cleaning and flushing of these systems can really help solve problems before they start. But it's important to understand what to do if maintenance issues occur. And the first thing there is isolate the cause. What is causing this maintenance issue? Is my system plugging? Do I have a failure in my solenoid valve? Are there polymer supply issues? Do I need to look at maybe having a strainer upstream? Obviously we want to perform the proper steps to remediate the issues, such as calibration or cleaning. And then if we say, hey, we think the system's plugging because of this, we changed it, we fixed it, but it's still plugging, the factory is a really good resource to have, right? We have thousands and thousands of installations in the field, and we've seen almost every single scenario that there is to be seen, right? So really relying on factory assistance is important. We're here to help. And many times, again, we've seen the issue before, and we can really help isolate it if it's something that's really tricky or isn't easily solved. The other consideration here is a maintenance contract. This is something where essentially you have a factory authorized technician go out on preset frequencies to help maintenance the system, do a full system check. The other benefit of these maintenance contracts is you can get deals on spare parts. This is a really good idea. It's not very expensive, and it really helps you maintain that system in its best operating condition. So those are really some things to address maintenance and operation concerns as they happen, and really to help prevent them from happening in the first place. So as I said, I imagine we're gonna have a little bit of time to have some Q&A here. It looks like we got about 15 minutes. I will try to do my best. I got to jump out of this screen here. Perfect. So if you have any questions, please throw them in this question chat here as they come up. I'll try to answer them. If there's anything specific that you guys would like me to go back and cover, or maybe cover in more detail, I'd be happy to do so. As we're doing that, I know that there were some questions regarding CEU credits. I know Mike will be sending out certifications after this. You know, this is, it does, you are able to get your certification credits off this presentation. So I know that that was a question that quite a few members had. We got one thumbs up and no questions. At least I got a thumbs up. That's good. Hopefully we get some questions here. I'm going to be hanging out for the next 15 minutes or so. So please feel free to enter any questions you have. Also, feel free, I'm going to put my information up here. Feel free to reach out to me. Again, my name is Luke. I got my email address and my phone number there. And I'm happy to address any specific questions you guys may have at your plant or in your design.
Hey, Luke. Luke, can you hear me?
Yeah.
So we're just so everybody knows, we have a new format with GoToWebinar, so it's different from what we're used to. There are some questions in there, Luke. Can you not see them?
No.
Okay. How about I'll read it to you and then you can answer it.
Sure.
The question's about high static mixing, hydromechanical of polymer, and not allowing polymer to age. Should an aging tank, a crucial component designed to hydrate and activate dry or emulsion polymers over a specific detention time, actually 30+ minutes, before injection slash mixed with biosolids?
Such a good question. What that really comes down to is a matter of economics, right? So coming out of a high-end two-stage, high mixing energy polymer blending system, you're looking at around 95 to 98% active polymer directly from the mixing chamber. What aging can do is it can provide you an additional, 2 to 5% activation. The problem is, well, not the problem, the question then is we need to be able to pay for that additional tank, mixer, and controls with that polymer savings we're seeing, that additional 2 to 5%. Generally, in smaller applications, it doesn't make sense, right? You're not using enough polymer for it to be able to pay off, for the ROI isn't quick enough to be able to pay off the additional equipment. When we're looking at larger applications, generally, when I start considering it as around 100 gallons per minute a solution, then we can start asking that question, do we want to add an aging tank here? Do we want to add a big batch tank here to realize those additional 2 to 5%? One really important caveat to that, though, is that we never want to apply additional mixing in that tank, right? And the reason for that is once that polymer has been exposed to the mixing energy and once it starts to activate or is activated, it's really susceptible to damage. So we don't want to provide any additional mixing. That 20 to 30 minutes of additional retention time is exactly right. That's kind of what we aim for. Some other areas where we may see that is in areas where you don't have tempered water, the water supply is very cold. Adding a batch tank can help in the polymer activation in that case. Other situations may be multiple application points. So you can have one larger make down system going to a tank, where you have multiple solution metering pumps delivering to the application points. So I guess the best answer is aging always can help. It's just a matter of, does it make sense in that particular application?
Okay, next question. Roughly speaking, what is the percentage cost difference or ROI for paying a premium for a mechanical mixing system versus a hydraulic one?
Minimal. The The consideration there is, right, you with a non-mechanical system, right, you're eliminating that mixer motor, and you're eliminating the impeller, right? Those are really the two things that you're eliminating from that system. The hydromechanical, or excuse me, the hydrodynamic systems have been around a very long time, and they're very good. They're very good design, but they are dependent on water pressure, right? So one of the things that we'll see is that if you have sufficient water pressure at your plant, and sufficient water pressure, we mean like 50 psi differential. So if you had 70 psi incoming, we wouldn't want any more than 20 psi back pressure. That gets us that 50 psi differential. System operates extremely well. In cases though where you don't have enough water pressure, you may need to add a booster pump, right? And adding that booster pump then kind of fills in that gap between the mechanical mixing and the non-mechanical mixing. Long story short, though, there's a very minimal cost difference between the mechanical, hydromechanical, and non-mechanical systems.
Awesome. Next question. Is there a specific type of mineral oil recommended for flushing and cleaning an emulsion system?
It's a good question. I don't know about different types of mineral oil, to be perfectly honest, but what I do is I just go to like Rite Aid or Walgreens and clean out their digestive lane and get a lot of bad looks as I'm walking out of the store. So I usually just use the ones from the grocery store that you can find in like the pharmacy aisle.
Related question, but different question. When using the mineral oil for cleaning, is once enough or do it several times?
Yeah, that's a great question. So generally, we want to do, if we're just filling up that calibration column, we probably want to do that multiple times, 4 to 5 times, fully drain that calibration column. If we're doing the recirculation process, we want to have that recirculate for 20, 30 minutes, right? So you're going to leave that system on recirculating for not hours, but you do want to give it time to fully flush the system.
Okay, next question. Is slightly lower quality water for carrier water, secondary dilution, acceptable?
Yeah, I think you still want to follow the same concepts as far as the water quality requirements. Really at any point during the mixing, or even if it's used as post dilution or carrier water, again, that chlorine can degrade that polymer efficacy. The solids can start reacting, with the polymer molecules. So we really want to follow the same guidelines. Again, it's not uncommon to use recycled water, reuse water. Ideally we're using potable water, but that's just, we understand that that's not really available in many cases. So, again, we're going to look at considerations there as solids. Do we want to have a strainer on there? We want to look at the chlorine content, stuff like that.
What type of screw press at a 0.6 mgd at a wastewater treatment plant?
The question is what type of screw press?
What type is best for a screw press, excuse me?
Oh, that's a great question. I can't answer that. I'm not a screw press expert. But I feel free to reach out to me directly via email. I'd be happy to put you in touch with some of the screw press manufacturers to help you on that one.
How do you know if you're mixing polymer and water correctly?
It's a really good question. It's another really good question. So the best way to know is by seeing how your process is performing, right? So polymer is tricky. It's really a science, right? You can judge activation based off of viscosity, but the problem we run into there is you can't take one polymer and compare its viscosity to a different type of polymer, right? Because different active contents, different viscosities with the polymer supply itself. So, you can use viscosity as a relation to the one polymer you're using and play with variables such as mixing energy, concentration, stuff like that, and measure your viscosity. It gives you a guideline. But the best way to understand how well you're activating your polymer is really the performance of your process. During startup, these are things that we're going to look at, right? We're going to look at your dosage. We're going to look at your solution concentration, and we're going to look at your mixing energy. And really what we're going to do is we're going to play with those variables until we find a fine-tuned area where your process is performing the best. And that's when we know we're making down the polymer efficiently. It goes back to, choosing a polymer system that has flexibility in its design criteria for you to be able to meet those different conditions so that you can fine-tune it to the process. I wish there was a better answer for that. I wish there was a device that you could just be like, I know I've activated my polymer 100%, but it really comes down to how your process is performing.
Excellent. Next question. Is it recommended to have a check valve downstream of the mixing chamber to not allow sludge to re-enter the mixing chamber / polymer unit?
Yes. I mean, well, that can depend on couple different factors, like how you're injecting or where you're injecting. If you're injecting into a pressurized sludge line, like generally you're going to use some sort of injection device that does not allow backflow. But yeah, it's not a bad idea to have a check valve, right? In some cases, especially if we're I think the main reason to have a check valve would really be like if we're injecting upstairs, you know what I mean? It's important to have a check valve on the discharge so that when the system shuts off, you don't get backflow from the head going back to the mixing chamber. Same thing can be said about sludge, right? So not a bad idea to have a check valve. It really depends on where you're injecting, how you're injecting.
Can you comment on when it is okay to direct feed polymer solution from the feeder / blender?
When it is, yeah. I mean, anytime. You know what I mean? It's these systems are specifically designed to feed inline, right? So the reason that these systems were created, the reason that these high energy 2-stage mixing chamber systems were designed was so that we don't need to rely on a tank and a mixer and aging time to be able to deliver solution to the process, right? So these systems are specifically designed to feed inline, right? They're specifically designed to blend in the mixing chamber and deliver directly to the process. With that, there are that's okay. No, with that though, there's considerations, right? Like water temperature, how much polymer are you feeding? So that's kind of stuff we'll look at like during design.
Next question. Where do you incorporate aging tanks and aging into the process to get effective polymer application?
Yeah, great question. As far as emulsion polymer goes, it goes back to what we were just talking about, right? Different considerations as far as water temperature. Generally, yeah, you're going to, instead of going directly to the process, you're going to be feeding from the make down system to a tank, and then you're going to have solution metering pumps feeding to the process. What we didn't cover was like dry polymer, right? So dry polymer, you always have to have a mixing aging tank, and you always need to have 2 tanks. And the reason that you need to have 2 tanks is really important is because we need to isolate the newly made down polymer from the polymer that's being fed to the process. Like dry polymer does require this full batch cycle of being wetted, mixed, and aged before it's fully activated and ready to feed to the process. So your tank 1 is going to be mixing and aging and wetting, or wetting and then mixing and aging. And then once it's done that full cycle, it's going to be transferred to your feed tank. As soon as that transfer is complete, you start making a new batch in tank 1. So as far as dry polymer is concerned, the batch cycle and the tanks are extremely important.
You mentioned chlorine. I'm sorry, next question. You mentioned chlorine damages polymer. Can you elaborate?
It's going to, yeah, the best way to elaborate that is it reduces its effectiveness. It actually damages the polymer molecule itself, right? So along that molecule, there's charge sites. It's an organic compound, right? So when chlorine basically is introduced to that polymer, it can start to degrade that polymer. You get less effectiveness out of that polymer supply. That's the best answer I have. I'm happy to elaborate on that more if you would like to send me an email, because that's also more of a chemistry question for the polymer manufacturers themselves, which again, I'd be happy to get you in touch and answer that question.
Next question is there recommended dilution water for the different types of polymer based on the percentage active content?
So there is, as far as the water quality, it's going to all really be the same guidelines. But as far as your solution concentration, that can change depending on what type of polymer you're using and your active content. The best example of that is cationic polymer, is you can make down at 0.5%, but an anionic polymer, generally higher viscosity, and we need to make down at generally 0.25%, right? So different types of polymers can dictate how much water you're using.
Well, we are at the top of the hour. I'm happy to go on, Luke, or do you want to call it and we can answer these questions via email?
We can do, how about 5 more minutes? I'm happy to do so.
Okay. For duty and standby dosing pumps, How frequently would you recommend alternating? Which pump is the duty pump?
It's a really good question. I think, I'm gonna need to think about that one, actually. I think that's gonna be one I'm gonna have to follow up on, because I think there's a couple different ways we can handle that. And I don't want to start throwing out answers here and then, fumble around. So I'll follow up with you on that question in particular.
Emulsion process and wastewater treatment into clarification. Recently installed into a new make-down polymer unit that feeds a day tank. Then from day tank, then feeds the process through a diaphragm pump. Both day tank and flash mix tank have mixers. Is that too much mixing?
Yes. Generally, we do not want to have so it sounds like there's a make down system, right, that is feeding to a tank. And in that case, we do not, after that make down system, we do not want to add any additional mixing. The reason for that, and again, I'm happy to follow up and send some information on this, but the reason for that is as the polymer is supplied and when it's first exposed to mixing, it's coiled up, right? So it's capable of standing a very high amount of mixing energy. And as that polymer activates, it elongates. And as it's elongating, it then becomes very susceptible to damage. So once you've done that initial activation, providing additional mixing really is just adding the potential for you to damage that polymer. It's really best just to give that polymer, since you have that tank should really be there just to give you additional residence time, right? You're just giving it a little bit more time before it's fed to the process.
Next question is, can you fully define neat polymer versus diluted polymer? Neat is in the emulsified raw state question.
Yeah, that's a really good question. So neat polymer is what is supplied from the manufacturer, right? So neat polymer is that mix of polymer, water, oil, and burning surfactant. It's the polymer as supplied. And then polymer solution is what would be referred to as the polymer after it's been mixed with water, right? So you may have think about it this way, we have 30% active content neat polymer, right? That's as supplied in the tote. And we're making that down into a 0.5% solution concentration. So the solution is after we've mixed it and added water, and it's what's being fed to the process.
For turbidities higher than 1,000 NTUs, an anionic polymer is better to dilute or as it is?
We can repeat that, Michael.
Yeah, so for turbidities higher than 1,000 NTUs on an anionic polymer, is it better to dilute or leave it as it is?
So I may be understanding this incorrectly, but the way I'm taking that is it better to dilute and activate that polymer before it's fed, or just feed that polymer neat? That's the way I'm taking that question. If I'm incorrect, again, please feel free to send me an email and I'll follow up. We want it, any neat polymer, right? Any anionic, cationic neat polymer needs activation, right? So we really can't just feed it neat. There are different chemicals, such as like some different coagulants, a polydadmac, other chemicals like that can be fed neat, but in particular to neat polymer, those do need activation.
All right. Let's see. When would it be indicated to replace the overwind?
To replace the overwind? Yeah,
Yes.
that's a good question. You generally don't need to, right? Unless there's it cracks or something, right? Like that's really there to, it's really just effectively conditioning the material that's in the hopper. So if there's any clumps or if there's anything like that, like it'll help break those up a little bit, but it also helps facilitate flow down to the auger itself. So it's not incredibly important for like the accuracy of it's not like an auger where, that if it wears, it can lose accuracy. Really, it only needs to be replaced like if it's damaged.
All right, well, we're 5 past the hour. There was a couple questions for me in there. Yes, I will be sending out a recording for this, as Luke indicated, there will be a PDH certification. So it's a certificate of completion. So that will be sent out tomorrow. The recording will probably be sent out in the next few days, if not early next week, the latest. Any other questions in the meantime, feel free to contact me or Luke. Anything technical, definitely contact Luke. We appreciate you guys all for attending. Have a great day. Look forward to seeing you all at the next webinar. Luke, do you have any closing statements?
No, thanks everybody. I'll be at Biosolids as well, so stop by. Thank you, everybody.